each of the committee members can have a couple of questions and then pass the baton on to the next person on the committee. And it's a tradition in ETH that we start with the person who's furthest away, which today would be Georg. So Georg, please go ahead.
Yeah, hello. Thanks a lot for this fantastic presentation and all the fascinating work you've been doing and presenting to us today. So I would like to start from the back with a question. So I have a question regarding this west of N, by the way, quite a funny name. So I'm wondering, how do I choose N with respect to the data set size that I can select from? And so that would be, there's some kind of theoretical results, and how when I start to choose too big N, I would kind of only take the extremes of my distribution. I would even sort of miss out the middle parts for my distilled model, or the distilled regulatory model.
Yeah, that makes sense. So, to be honest, I don't have a theoretical analysis of performance as a function of N. So, from a theoretical analysis, I don't have this answer. In terms, practically, that's definitely a concern that we had, which was maybe what we tried to address in this third plot here on the right-hand side, which was by taking N very large, are we taking responses that are very far from, say, the mode of the distribution, and so ending up with responses that are out of distribution with respect to the language model. What we found is that, yes, there's this downwards trend, but we're still orders of magnitude more on policy than the human preference data we started with. So I think definitely what would be a concern is if we start going below this black line and becoming less likely than even the preference data we started with. And so maybe then the best and the worst would be maybe gibberish, or the best could start hacking the reward signal, and these new synthetic data pairs are not as helpful. In practice, even with N equals 64, which I think in practice is too large for a real application, we didn't observe this. So I think hopefully within this range for the data sets we worked with, that wouldn't be so much of a problem. But a good point would be maybe, like you said, depending on the data that you start with, if you don't have very much data to start with and your preference model isn't very accurate, then you could start hacking the reward signal maybe with less data. And so that could be a challenge that you're facing with. So I do have a slide that's really showing the gains with West of N. Let me try to find it. As a function of the quality of the initial teacher model. And so there's this clear trend that shows the better your initial teacher model, the more gains you get with West of N, with here a bit of an outlier. But yeah, I think that's something also to keep in mind in terms of pushing N to the extreme, is how good your initial reward model is, and are you going to start hacking it very soon.
Fascinating, really interesting, cool.
Yes.
My second question would be on the label smoothing part. So I was wondering, if you make this smoothing operator quite long, then you're kind of trying to, of course, predict the event quite some time in advance, and maybe there is no signal yet. So I was wondering, how much do you increase kind of overfitting or spurious correlations that your classifier would pick up, because you're kind of asking it to predict something that is not even visible in the data. So with respect to your classifiers.
Yeah, that's a good point. So to be honest, we haven't looked at performance necessarily changing the horizon H that we assume, because we just were playing with benchmark data where the data was labeled according to a certain horizon, and so we didn't play with this too much. I do think that if you start increasing the horizon too far, then you might not have so much signal, and then, yeah, I'm not sure what you would pick up on to be able to predict whether the event occurs. Like you said, probably confounding. And yeah, if you do label smoothing in these cases, maybe you'd still get some gains in the sense that by essentially putting a lot of the weight, making the model really focus on these data points that are close to the event, allow the model to try to identify the discriminative features close to the occurrence of the event, such that even if we're very far, maybe we're still able to pick up some signal. But definitely, I think if you increase the horizon too much, yeah, I'm not sure what the performance would look like, but yeah.
Yeah, and the other question that I had, thank you, yeah, so this makes sense. So in the results that you had, you were able to get recalls of about 10%, if I understand the labels correctly. So I was wondering a little bit, is that number correct? Is it, maybe these are different numbers,
So definitely, so maybe you're thinking of this slide, which was the performance as a function of time. So I've simplified it in my slides today, but that's, the fact that when we train with binary cross entropy, we're able to get a reasonable recall very close to the event, but then as we get to this very noisy region where the label switches, we have about a 10% recall. That's, indeed really showing that we're not able to pick up on much here. And with the results that we have in terms of performance as a function of time, we don't get necessarily a huge improvement in performance in those regions, so maybe there is just not enough discriminative signal here to really pick up on this. But the gains in those regions are particularly large, so we're able to improve prediction performance here. So I think, that's kind of going along the direction of what you were suggesting earlier, that with the horizon baby being too far, there just isn't so much signal to pick up on, and so the model struggles. I think an interesting extension on this has been done by people in my group, so Hugo, who's over here, which is rather than try to just predict this early event prediction label, try to do survival analysis and try to regress how far is the occurrence of the event going to be. And they find that they can get better event recall, so overall, rather than just this time step level analysis, overall better ability to pick up on the fact that events are happening by slightly changing the formalism of the task and looking at it more from a survival analysis perspective than just binary classification at every time step.
Thank you.
All right, thank you. And let's continue with Georgia.
Yes, so first of all, thank you for the presentation. It was really very good work and amazing work. So my first question is also on the Western work. So I think that some of the questions also one question that was asking was also mine, and so I will go with the other ones. So because the first one was how good needs to be the preference model at the beginning, and sometimes you answer that, and the idea is also I thought that to have sort of a method where you are involving also the humans during the process, so to get better preferences in some parts, in some regions where it's more uncertain the model.
Okay. Yeah.
And to have something that is not asking all the preferences that you need, not for the humans without this Western, but having also the loop.
Yeah. I think that's a very interesting question. So the fact just too many extra slides. So the fact that we observe that this quality of the labels in the human feedback data that we have is so low doesn't necessarily suggest that the human feedback data is not helpful. It's just that they're closer to each other in terms of the decision boundary and how much better is one side over the other. So I think that's one thing to keep in mind, in that here what we're trying to do is maximize the quality of the labeling because it's this self-training procedure that exploits the model itself. But in terms of human feedback data, it might not be as helpful to have a human label the best and the worst because we're quite confident that they're better, rather than two responses which are close to each other in terms of preferences, and so we're not really sure how to discriminate them. So I'm not sure that this approach would necessarily be the best way to try to collect human preference data, since if we assume that they have the ground truth, it might be better to discriminate responses that are close to each other in terms of preference. But yeah, I'm trying to think. It could still be helpful to have feedback data, I think, at a post hoc stage, where if we look at this plot that we have in my thesis, which is showing that if we filter out some of the data by checking after we take this best and worst event procedure, if you just look at this left-hand side plot, if we filter based on the confidence of the teacher model, so either we keep all of the preference of the synthetically generated data, or we remove all of it, but to a certain extent we filter some of it out. for instance, if the teacher model is not very confident, we still get an edge in performance, so an edge in, so we were able to get this gain in accuracy if we filter out some of the data, which at this stage maybe you could use the human feedback in the process, for instance, on the data pairs that the teacher model is not very confident on.
Exactly, to improve the teacher model.
Exactly. So I think those could be a way to identify data points that we're not totally confident on. We think they should be, the best should be much better than the worst, but because the teacher model is not totally sure, there's maybe some signal here that would be useful in terms of human feedback.
Yeah, because they're doing something similar also like in robotics with images. So basically they're looking at two different images like of robotic simulations and then like asking directly like to allow them to create like the preferences from images, and they're continuing like without like human preferences to do it.
Yeah. And
the problem clearly is that how good is the model like in doing the preference part. So it's similar here.
Exactly.
The starting model is
pretty good, so that's why we get these gains.
Better, but otherwise, like I think that's
exactly.
We continue to like create errors to errors.
Exactly. Yeah.
So okay, so this was my first question. The second one is on the Daltic uncertainty.
Yeah.
So it was on the experiment that you did with like the real experts.
Mm-hmm.
How did you like perform the experiment, and how did you like also communicate with them what is the meaning of confounding and
yes, that makes sense.
Because it's really complicated.
Yeah, it was, and I think there's a lot of things to be improved there. So because we don't have access to the real environment, what we had were both in this paper and in the poetry paper that we have in my thesis, we asked a few clinicians to tell us, in one case, what treatment strategy they thought would lead to better outcomes in terms of the patient. So not necessarily explaining to them the whole confounding idea, but just asking them which of two treatment policies they preferred. And then we asked them to do pairwise comparisons. So the data looked something like this, where we showed them some high-level overview of the key features of the patient as a function of time, and then we gave them more or less contextual information that corresponds to our confounder. So essentially, if we remove some of this contextual information, because this information is important to taking a certain action, they're going to act as confounders. And then we asked the doctors, would you take a certain action or another in terms of improving the patient outcomes, where one of the options was the one recommended by the policy learned by our algorithm, and the other would have been the one from the imitation learning policy. Mm-hmm. So that's how we did this pairwise comparison between behavior cloning and the policy learned by our algorithm. And there we collected a lot of this data. I think there was still a lot of noise in the process and a lot of inter-annotator disagreement. So I think, maybe with like a more rigorous survey, you could get more, slightly less noisy, more signal in the results. But that's how we collected this feedback, where we were able to tell, okay, if we're missing a lot of information, so we're in the confounded setup, then they tend to prefer a conservative approach that if you don't know the background of a patient in terms of the diagnostic, the reason why they're in the hospital, then maybe you would take a conservative approach to treating them. Whereas if you know everything, then maybe they'll just reproduce.
Okay, so basically confounding were like information about the patient.
Exactly.
Okay.
Yeah.
Okay. So they have like some information that are like removed and some other information that have like.
Exactly.
Okay.
Yeah. That access confounding. Yeah.
Okay. So
Excuse me, I did not quite hear.
I say that's.
Let's move on.
Move on. Yeah.
Okay, all right, thank you. Let's move on to Bernhard.
Yeah, so very nice talk, very nice thesis. I would like to maybe also start from back the work on the LLM application in more like the different responses or expressing preference. So I'm trying to construct a connection to your work about the uncertainty.
Right.
Maybe it's not going to work, but I'm interested in your opinion. So, language models can have different personas, and depending on the context, they can give different kind of answers to the same immediate question.
Mm-hmm.
So it feels a bit like maybe also, depending on the persona, maybe the ranking could also depend, ranking which answer is better to depend on what person a language model is simulating at a different point in time, which you may not know when you're ranking. So there might be I wonder if there might be also some issue of confounding there. And I don't know how you see that, and also if I don't know, do you see any field? Would it make sense to model that? How would you do it? How do you think about that?
Yeah, I think that's an interesting question because there has been some evidence that these preference models are often rely on spurious correlation. So for instance, they're going to prefer a long response over an equivalent response that's just shorter because there is this bias in the data, and the preference model has picked up on these spurious correlations that I'm not sure if it's explicitly confounding, but there's clearly some like wrong causal link that's picked up by the model, and that would then definitely, I think, with this approach, and this approach of self-training on the outputs of your model, be amplified with this self-training approach. So that's one of the criticisms that we had from some of our reviewers, which were you could potentially be amplifying bias from your preference model. Because this idea that you're getting the gains that come from how good is your preference model means that if your model isn't very good, then you could kind of accentuate those biases. In terms of trying to address this within the RLHF literature, I'm not sure there's been explicit, like theoretically motivated work from the causal perspective, other than just adjusting for the data that you're training with and making sure that, for instance, you're correcting for these biases that lead to a preference for a longer response. But also within the preference learning framework, I think it's also an interesting problem because if you look at simply from the Bradley-Terry model fitting your reward model, essentially you're considering the returns over the entire trajectory, which if you get just feedback on the binary preference for a trajectory, makes it very hard to assign credit to individual state interactions within a trajectory, which I think, again, has been shown to within the preference learning framework, lead to spurious correlations and identifying, for instance, that there's some features that are more present in the data that's more typically preferred, even though that's not necessarily the discriminative signal there. So, yeah, of the few works that I've seen within like collecting causality and preference-based reward learning, I think that's also an interesting one in terms of assigning the credit and the reward function, discriminating it within individual state action pairs.
Thank you. So maybe I can also ask about more specifically about the delphic uncertainty. I think it's very, very interesting concept. I guess I know presented the conferences to discuss with people. I assume some people challenge you as to whether it's necessary to have this concept. I mean, maybe from this point of view of the statistician, one could say, well, there's other learning notions. If you have how is this different from just choosing a wrong model or having a fire or something like that? Is it necessary for a fundamentally different notion? Yeah, how do you think about that?
Yeah, so the way that we've tried to separate this is by really, is it this? No. Yes. Really trying to split this delphic uncertainty, which we relate to uncertainty with respect to the structure, from the statistical sources of uncertainty. So we find that with this theoretical analysis, if we have infinite data and no stochasticity in the environment, then the statistical sources of error should go to zero, whereas this uncertainty with respect to the structure remains even in these extreme settings. So there is definitely something here in terms of it's not exactly the same as epistemic uncertainty, which goes to zero with infinite data, because confounding doesn't disappear even with infinite data. Now, it's been challenged in terms of how does it relate to other causal framework for dealing with hidden confounding bias? So for instance, is it a form of sensitivity analysis where you're making some assumptions about what are these potential confounder compatible world models, and then you're measuring the uncertainty with respect to this? And I think there's similarities here, and the sensitivity analysis framework could be plugged into ours in terms of just looking at the confounder models where we are within this sensitivity analysis assumption that the confounder doesn't affect the policy by more than a certain amount. And in this case, just constrain the set of compatible world models that you're considering because you have this partial identification assumption about the variation over the confounders. So I think that's been one of the questions that the more causal people came up with in terms of how does this relate to the more causal inference strategies. Yeah.
Thank you. And maybe last one. What if you have incomplete information about the confounding? You have some proxies or something that tells you something about the confounding. How do you take that into account?
Yes. Yeah, that's a great question. So the way that we tried to address this was by having a model for the confounders that's still data-driven in the sense that we start from a prior, and that's going to be, depending on what prior we take of the confounders, going to determine some of the variation between these world models. But then by the fact that we update our estimate of the confounders by saying, okay, the entire trajectory shares this confounder, so there is information here that we could use to improve our posterior estimate. And then we use this distribution of the confounders for the policy and Q function models. But in practice, it means that if we are in the identifiable setting where we have some information that allows us to learn the confounder, these models should converge to the same distribution over the confounder, which means we're not going to have this disagreement between the world models, which in theory, again, should mean that we do not have any source of Delphic uncertainty. So that's in the setting where we have partial identification or perfect identification from the proxy, the world models should all be the same, and so we have no uncertainty. That's the theoretical framework. In practice, whether we're really able to converge all of the same models for the confounding is, I think, something that would have to be tested in practice.
Thank you.
Thanks.
Okay, thank you. Then let's move on to Gunnar.
Okay, first of all, thanks for a very nice presentation. Very clear and nice. Maybe there's a lot of questions which were asked already, so maybe let me take a high-level perspective here. So on part 3, right? So you learn the reward, you simulate the environment, you simulate the policies and so on, right? So, but in part 2, right? So you avoid simulating in some sense, right? So and you do the offline IL. So if you would go back today to part 2, is it still what you would do? Or would you maybe indeed go back to trying to simulate the environment and then do online RL with this environment? That's what you essentially do in 3, right? So that's part of the game there, and you have to do it in order to learn the reward, but you haven't done it in part 2. Isn't it what we should do?
I think it might depend on the application. I think in practice for medical application, that could be the better approach. You have limited amount of data, and model-based approach can really help with sample efficiency. What we proposed with this method was relatively general in the sense that if we just look at this variation over the compatible world models, you could assume that you have a model-based approach where you learn the confounded distribution and then the transition, reward, function, and the behavior policy. So you could use this entire framework within a model-based approach. It's just that in practice for our analysis of this Delphic uncertainty, we said, oh, we don't necessarily need to bother with training both the transition and reward model. Let's just learn the Q function and the policy, and then we do our counterfactual estimation. So this was just a practical motivation in terms of making our life easier there, but I think that would also be definitely a method that we could do, and hopefully the results would translate in the same way. There were model-based approaches that we considered in terms of applying the pessimism with respect to the reward function, for instance, in terms of instead of the Q function. That in practice also worked well on this data. It's just that we didn't necessarily focus there.
Good. And so, the most complex is part 3, and what is missing, let's say, to apply it to, let's say, a real medical setting?
So part 3, I think first this method that's motivated by language model applications could potentially also help in non-language model problems in the case where you have, say, a high-dimensional action space, and so you're outputting different actions for a certain state, and you're considering with an initial reward model, can you then rank these and do this best and worst approach? So maybe that would be one way of translating this to like a sequential, traditional decision-making framework. With this method that we proposed, we did apply it in the sepsis simulation where we were motivated by the clinical problem. In practice, we did everything in simulations where we have the ground truth reward signal, and that's, for instance, what gives us the expert feedback on the preference. So if we were to do this within a real medical application, we would have to have the doctors available, figure out a way to represent, maybe a bit like this survey we did, but I think there was so much noise that maybe try to think about this in a more clever way, how we represent the state of the patient, then how do we collect this feedback of what is a better trajectory than another from the doctors, and then hopefully the rest should be as straightforward as it can be on medical data in terms of learning a transition model for how the patient evolves, and then building our estimate for how good is a certain action to take in a certain state. So I think the challenge would be really this collection procedure with real humans, which we really avoided by having access to real simulated environments.
Okay, good, thank you.
Thanks.
Okay, thanks, Gunnar. So we have still lots of time for Q&A, so let's go for a second round at least. And so let's get back to Pierre then.
Great, yeah, wonderful. Yeah, so maybe we stay here at this Delphic section, which is really quite interesting to me, and I have a few questions there. So one was, you partly answered, I think, to Bernhard already, was about how do you manage to sort of learn all possible models, and to me it looks like you use some kind of operational approach, is it correct? Or?
Yeah, that's right.
And I was wondering whether you have observed some kind of mode collapse type of behavior of these models, and as maybe just this.
Yeah, yes, we did. So definitely, yeah, that's stuff we observed. Then in practice, we ended up taking the models that still were giving us reasonable estimates for some confounded distribution, and then some mapping to the Q function and the behavior policy. There was also some work that was flagged to us by reviewers that said, if you're assuming that you can do full identification with these variational approaches, then there's been some work that shows that you're really dependent on the initial modeling assumptions that you make in terms of your prior and how you fit that to the output variables, which we did find to be the case in the sense that by taking different priors, different dimensionalities for the confounders, we were able to retain this difference in the estimations with respect to the policy we were interested in. And that's kind of what we tried to measure. So the fact that we're not able to identify necessarily exactly the confounded distribution and collapse to the same thing is what we're trying to measure with this measure of uncertainty with respect to the structure of the contextual MDP. But yeah, so I think if you were assuming an identifiable setup and assuming you were able to collapse the confounded distribution always to the same one, then because of what this paper showed, you might have some trouble always reducing the Delphic uncertainty to zero. So what we proposed was one practical method for formalizing these compatible world ideas. With this, I think in practice, depending on what assumptions you might want to take, you could probably do better.
And so the follow-up question on this topic is, you measure the uncertainties, and if I understand correctly, you use an ensemble modeling technique, right?
Yes.
And so I was wondering about sort of your assumption about the noise of the uncertainty model.
Yes. So it was quite an expensive procedure in our method of trying to separate out the uncertainty so that we could really measure, does epistemic uncertainty increase when we have less data, Delphic uncertainty when we have more confounding, so we could separate these different types of uncertainty, which I think in practice wouldn't necessarily be required because you're always trying to penalize epistemic uncertainty as well as confounding uncertainty perhaps. So you might not need to do this expensive procedure of having world models and then within these world models the ensembles of probabilistic models, which is how we tried to separate this. So every output of our Q function was a probabilistic model that outputted both a mean and a model for the variance. And then we did an ensemble over this and a set of world models that were compatible, which was quite expensive, I think, for practical application. And again, I think there's been also some methods that try to improve the robustness of these uncertainty estimates from a statistical perspective. So I think also, Georg, you have some work on trying to improve the training of probabilistic deep nets that I think, for instance, could be fit within this framework of making sure we get calibrated uncertainty estimates.
And then you were using simply the variance of these ensembles, so you kind of assume that you have some kind of a Gaussian
Yes.
uncertainty,
Yep.
right? Do you think that is particular for the Delphic one, where you do structural changes? Do you think that is kind of related, but I say how well does it fit? Because I guess if you're changing the structure of your model, you might probably end up with very different predictions. So I guess they would not necessarily be Gaussian.
Yeah, that's a very good point. We've not, really looked beyond the Gaussian assumption. In practice, we did this separation of, aleatoric, which was just the expected output of the variance of our probabilistic model, and then the variance over both the mean and variance outputs of every ensembles, and then this variance over the compatible world models. But we didn't look at anything beyond variance over the mean estimates within the ensembles. I think that's an interesting question.
Do you have an idea how you might otherwise? I mean, if you have, I don't know, if you have this ensemble number and every one of them output the distribution, how you would maybe otherwise measure this variance term?
So I guess, some kind of measure of the disagreement between the different distributions. So say taking maybe the maximum of the KL divergence between two estimates of the world models would be one strategy.
I hadn't really thought too deeply about it,
No,
but that makes sense. Good. Okay, cool. Do we have a third round, or should I go?
Sure. And you can also continue now if you want, whatever you prefer.
Maybe let's just go on, and then I have another question if we need it.
Okay, sure. Okay, then move on to Georgia again.
Yes, so again, in this problem, basically you're like solving like a very complex problem because it's not only on a line setting, but also it's a partial observable in some sense. So in your opinion, which is like the performance that you want to maximize, that you want to achieve? Because clearly, you have many information that are missing since you cannot interact with the environment, and so you have some information on the state that you cannot observe.
Yeah.
So what is the performance that you want to achieve? If you want to think about for example, the regrets, what would be something that would make sense?
So really what we looked at in terms of the simulation where we have access to everything was performance assuming access also to the confounders. So is the policy that we get robust to the fact that even if the confounders is absent in the data, but you have access to them at evaluation time, so you can measure to what extent you're confounded, and the policy that you get allows you to be independent of this confounding. So that's how we try to think about it, with also this just penalization of the Q function, which is really try to downstream just obtain a policy that achieves good returns, minus the fact that being aware of the fact that you have this uncertainty. So we're not also optimizing for worst case returns, which would be, I guess, if you consider the Q function of the world model that predicts the worst possible Q function for the policy you're optimizing at this stage. So that would be maybe a way of trying to have something that's fully robust because you're optimizing for the worst case Q function. In practice, we're saying, okay, let's, with some hyperparameter, that's kind of how we trade off this robustness and the exploitation, determine some way that we're going to weight this uncertainty, this penalization on the Q function, and then we get a policy that is robust to some extent.
So to be like pessimistic but not too pessimistic.
Exactly, modulo this hyperparameter, which is this great open question of fitting hyperparameters in offline RL, and that's also just very much a PhD in itself, right? Like,
yeah. And also, like, coming back in some sense to what Gunnar also asked, so like here, like in some sense you can think about what you've done, like also in the CMOPRL paper. Think about it, you have like a system that you can like ask to the humans instead like of like your information about the preferences, but about any information about the compound.
Yeah, that's a good point.
Have you thought about like what would be like a good method to do it?
Yeah, I think that ties in also to an initial work that we both were thinking about, which was collecting feedback on the transition function itself. So why just collect feedback on the fact that one trajectory is better than another if you're in the offline setting, but you still have an expert that knows a lot about what the transition function should look like? You could get feedback on this, and that could be a sort of proxy environment or proxy intervention that gives you information on the transition model. So yeah, we had some promising results on the fact that integrating feedback on the transitions was helpful in general beyond just offline learning. I guess with this problem, we could have some kind of measure that's explorative with respect to delta uncertainty, so asks the transition feedback in regions that we would expect to have potential confounding such that we're able to improve our estimate of the transition model there. I think could be, yeah, interesting.
Okay, thank you.
Okay, thank you. Bernard, any more questions?
Yeah. So Alizée is now one of the world experts on the interface of causality in reinforcement learning. So I'm interested in your opinion as to, I mean, we've seen that reinforcement learning has become super popular, but the impact of causality has been relatively limited in reinforcement learning. I don't think it's responsible for that. Is there something to change there? Does it go into research, or does it mean we have to stop doing this kind of stuff?
No, I'm still very excited about causality. I think particularly in settings where you have limited amounts of data, for instance, you can really improve the sample efficiency of your process, hopefully, with methods that are grounded in causal inference. So I think things like maybe building a model of the world that's causal, with either with some knowledge that's injected by domain knowledge, or with the causal discovery approach, really try to improve our estimate of the world model, would be a way to improve the sample efficiency in RL. Again, in these applications where we don't have so much data, we don't have access to the environment, so it's challenging to do RL in the traditional, very data-hungry way of just trying things out in the environment and seeing if we're doing better. Yeah, so I think also with one thing that I was thinking was with very high-dimensional action spaces, if you're able to, again, build some hierarchical model for how certain action affects certain dimensions of your state action space, it could be interesting, again, here to have some causal method that tell you, okay, certain parts of your state are independent from a certain action, and so that, again, improves the sample efficiency of the process. So, yeah, I'm still hopeful that causality is going to be helpful in those applications. Ultimately, I do think it's a very similar language for addressing the same problem, which is this idea of counterfactual query. So what would happen if I did a certain different action in the environment? Would that lead to a better outcome? And so, yeah, I think it's been interesting to try to translate some of the works that had been done in causality with, say, importance-weighted regression, and seeing that you get very similar results in offline policy evaluation with importance sampling, for instance. So I find there's a lot of overlap in the problems and the strategies developed, but sometimes it's also just a challenge of trying to find the right language to understand each other and kind of bringing the breakthroughs you get in one field in the other and vice versa.
Okay, thank you.
Thanks.
All right, Gunnar, how about you?
Yeah, I don't have many questions, but here maybe one. Now you're at the end of a PhD, right? So let's say you are not at the end, but you're halfway through. What would you do the other half?
Yeah, so I think, I mean, there's many interesting things to do on, I think, lately, just because I've been focusing on this reward learning framework, I think that's a very important problem in terms of how do we define the objective we want to maximize for a certain problem. And there, try to think about the sources of feedback that you can leverage, what type of data you can use to improve this process. So maybe that would have been, I think, an extension to some of the work that we've done on that side of things.
Is that so complicated in the medical domain to say what is a good reward? I mean, I can say this patient is healthy, this one is not, so I'd like to make it.
Yeah, but how do you formalize that with a function that tells you how good is a certain action to take, given the state of the patient?
Yes.
If you've got, okay, you want to get to a certain healthy state, but you also want to, so you want to make sure they survive, but you want to make sure they don't have comorbidities, you want to maximize their comfort. You've got very different things that you're trying to optimize for jointly. And I think manually designing this is very hard. So you would have to have some way of learning this in an efficient way, with feedback, with demonstration data, maybe with some way of injecting domain knowledge. And I think that's also an interesting direction, would have been to see to what extent we can exploit maybe some of the knowledge that's either available out there from doctors and try to find a way to inject this within models of decision making, or even language models. They have so much clinical knowledge nowadays. How can we exploit this in a way that again improves the efficiency of whatever model we use?
I mean, there's so much knowledge out there, so
and we just focus on a small data set of patient trajectories, and we try to learn everything from this. But it would be interesting to think of ways to maybe exploit everything we already have out there, and then on top of this, just maybe specialize things to a specific hospital or task.
Okay, so essentially we could go from part 3 back to
maybe
some.
Yeah.
Okay, thanks. Thank you.
All right, so then let's see whether there are any questions left. Anything else from you, Georg?
Yeah, I had some other questions, namely, particularly for the last part. So, right, we use reinforcement learning mostly because we want to work with the stochastic environments, and we have infinite horizon problems, so we want to have value functions, right, to have our cost to go for potentially very long or infinite horizon problems. But let's say in this healthcare domain, our horizons are not terribly long, right? So I'm wondering, what are your perspectives on using instead model-based planning methods with your learned lot models, using all this uncertainty stuff and so on, but actually do sort of test time compute rather than distilling policies that would do the right thing? You think that is?
Yeah, I think that's a great question, and would also tie in a lot with some of what Gunnar's group has been working on, which are these event prediction models. So really these model-based, these models of the evolution of the patient. I think there's potential work to be done in terms of really making sure that we get these models to be robust to different treatment strategies, because I think that's not necessarily being a focus so much as just predicting what is going to be the evolution of the patient. But if we now change the policy to say the one that our algorithm is considering, are we still robust? Is the prediction still accurate with respect to how the patient is going to evolve? So yeah, I guess that would require making sure that we're thinking about the treatment in the correct way. But maybe this would be the way, again, to leverage all the knowledge we have about how patient physiology looks like, what we would expect from them, and then imagine within this space what treatment would be better. And in a nice way also maybe to inject some causality in there in terms of what the treatment of a certain, what the effect of a certain treatment would be on a patient. So yeah, definitely, and I think that's also kind of the motivation, perhaps some of this model-based simulation approach, where that requires building a very good model of the environment on which we could collect the preference feedback, as well as maybe the transition feedback from the experts. So maybe that would be a nice way to kind of pool everything together, getting feedback from the experts, injecting some knowledge, putting causality in there. But maybe it's a salad of everything I've done.
Right. So I'm wondering, what are your thoughts on combining these different quantities? So on one side, you want to have correct prediction, let's say, of your model, but you want to not leave your region of certainty. So you have somehow to balance these two drives, or like these two needs, right? And they have typically different physical units, right? So your uncertainty is maybe in some kind of KL divergence, or here there's space of your predicted distributions, whereas your reward function that you want to predict has a completely different unit. So how did you manage to bring them all together?
Yeah, Gunnar had the same point a few years ago, which was, okay, here we're considering the variance and we're penalizing something that's proportional to the variance of the Q function, which is not the same unit. So I don't have these results here, but actually we did compare, oh, what if we take, say, the square root of the uncertainty, does that look better? And after having scaled for the hyperparameters, we didn't find that there was so much of a difference in terms of the policy that we ended up with. So yeah, maybe the underlying question is, how do you fit your hyperparameter within this trade-off of robustness and exploitation? In terms of specific scale, or say taking the square root, we didn't find a huge difference in the performance of the policy downstream.
Yeah, I guess it is equivalent, right? So if you have a hyperparameter, that determines
sort of
one, so the trade-off.
But yeah, within say a theoretically motivated approach, which was the algorithm that we first proposed with Georgia, is theoretically motivated. So we have the theory determines what is going to be the hyperparameter. So how wide is our uncertainty function, and how to penalize it. So there's a sort of ground truth. In practice, it depends on terms that are impossible to estimate. So things that depend on the complexity of the function class, etc. So yeah, in practice, it would have to be tuned on some validation set, or some external measure of how good is your policy.
Okay, thanks. Any final questions from you, Georgia?
Only one, like, is curiosity. Since you work now also on the LLMs and these kind of things, and there are like all the problem reward alignment. Do you think that your perspective, since you work also in causality, can give you like a different perspective on how to solve like this problem, or do you have some ideas on how to integrate it?
Yeah, I do think so. Like we discussed with Bernard earlier about these spurious correlations that the model picks up on, and that's still very much a big problem in terms of avoiding hacking of the reward model when you fit the language model to it. So I think the methods that people have converged with to try to harmonize the data to avoid these spurious correlations are motivated or very similar to the methods proposed in causal inference of weighting your data and trying to adjust for the fact that you might have confounding. So yeah, I think it gives me this perspective of what would have been the methods from this literature to try to address this problem, and hopefully, yeah, they also translate to some other examples that I'm going to face in the future. I do think so. I've been trying to think of maybe a way that maybe SIMO-PRL could translate to a language model application. And here, I'm not sure to what extent it would be easy to translate it, because it essentially relies a lot on the sequential process, so not having access to the transition model. And as far as RLHF is done right now, it's still very much a bandit setting where we don't need the transition model, so it's just maximizing the reward of a single response to a given query. But maybe, say, within agentic behavior, aligning agentic behavior of LLMs, where there is really this multi-turn approach and achieving an objective at the end of maybe a step of interaction from the language model, there may be something that builds a model for how the language model interacts with the world could be useful in this way, and then maybe these more sequential decision-making approaches could translate to language model alignment. And that's kind of the multi-turn setting that I think would be interesting to compare to all the methods that have been done in traditional RL. But,
yeah, and like since you also work on two different applications, in some sense, also like I mentioned in terms of challenges, what are like for you like what is like the main challenge that you're seeing, like for example, like in applying RL to medical data, instead like on like LLMs where you have like access to all?
Yeah. So yeah, that's really been this motivation behind this whole focus on offline data, which again in LLMs is not so much of a problem with not even having to require an environment. I think also with medical data, there's data challenges that are fundamentally make it very hard to apply these methods to a real world application. And that's maybe why I've focused more on methodology, is that we still have very limited amounts of data, unlike in language model applications. The problems are often not very well defined. So we had one project where, with people from the University Polytechnico di Milano, we tried to do reinforcement learning specifically for treatment optimization in intensive care, and half of the project was really trying to define the problem, what are the treatments we're trying to optimize for, what is the reward function, again, that we're optimizing for. And so, yeah, I see that that's maybe the first hurdle to really bringing RL in practice to these medical applications, is really finding the problems where this is particularly useful, making sure we have the data, and then hopefully these methods can straightforwardly be applied. But that's maybe the first step.
And apart from the data, there are also other problems.
Evaluation, of course. So again, kind of have to determine to what extent you find that the policy that you end up with is useful with some methods that are again biased because you're offline. Yeah, I guess that's how I see it. And again, like, there's all these steps in the process of maybe building a model of your environment, and how do you validate it? Are you confident that you're really identifying causal links and not necessarily just some spurious correlations? So, yeah, I think the fact that we're offline brings all sorts of challenges in terms of dealing with the confounding, and then the fact that when you're evaluating, your evaluators might also be biased, make this quite difficult.
Thank you.
Okay, no further questions?
No.
Okay, Bernard, how about you?
I'm happy, thank you.
Okay, thanks. Gunnar?
I'm good, thank you.
All right, great. So then we can close this public part of the event. I would like to ask everybody except the committee to step out of the room and to leave the Zoom call. And we'll call you back in once we reach the conclusion. Thank you.